Hi everyone. I kind of filled in some of the stuff that I wanted to write out so that you wouldn't have to wait for me to write it all out. So for 13.3, we're talking first about arc length and then curvature, and then I'll put a part 2 up because this section is kind of long, talking about normal binormal planes and such. Okay, so first arc length. In R2, the arc length can be found with the formula S equals the integral from a to b, the square root of dx dt squared plus dy dt squared. And this is all with respect to t. So that should look familiar. It's equivalent to other formulas that have similar characteristics. And these are all coming from Pythagorean theorem, pretty much, adding up little pieces. So let's look at R3. R3's formula is pretty much the same. We just have an extra dimension to deal with. So the arc length, which I'm using S to represent, is the integral from a to b, the square root of, we're going to take dx dt squared, add it to dy dt squared, and then dz dt. It's just kind of a natural extension, and then this is all dt. So I want to take it, let's look at a little bit here. We're going to have like this dt squared in the denominator. The square root will kind of undo that, and then the dt, so we have a dt in the denominator that also is going to cancel with that dt. So you can see that how the differentials work out here. And if you notice, this is actually the same as the integral from a to b. That square root of the differential, or the different derivative squared, is going to be the same as the magnitude of r prime. So this is a little bit more compact and easier to remember. So if we have some curve, let's say this is r of t. What we're doing when we calculate arc length, so let's say this is t equals a, and we're going to do t equals b. What we're literally doing by taking the derivatives, we're taking these little lengths, these little tiny arc lengths, that's what we're doing with the integral, is we're breaking up this curve between a and b into infinitesimally small little pieces, and we're adding up infinitely many of them. I think that's spelled wrong. Many. Infinitely many little tangent lines. Okay, so here is our formula. And let's proceed with an example. So for this first example, find the arc length of r of t from t equals 0 to 1. If you want to try it, go ahead and hit pause. All we need to do really is we need to find first the derivative, which is 12t to the 1/2, 6t. Then we're going to need the magnitude of that, which is going to be square root of 12 squared plus 12t to the 1/2 squared plus 6t squared. That's going to give us square root of, I'm going to rewrite this. Let's see, I've got 36t squared plus 144t plus 144. We can factor out a 36. And if we factor out the 36, let's see, 144 divided by 36, I think that, let's see, that's 12 times 12, right? And this is 3 times 4. And 3 times 4. If we take out, this is being silly. If we take out the 12 and the 3, we're left with 2 4s, so we're left with 16. So we've got, is that right? That isn't right. It should be, I'm cheating now, I'm looking at my notes. It should be t squared, if we factor out the 36. Okay, I'll stop cheating because I don't see where I am. We're left with 4. Sorry about that, I'm glitching. Okay, so then this is going to be t plus 2 quantity squared. And we can actually take the square root of that. So that's just going to be 6 times t plus 2. So now we can set up our integral for arc length. It's going to be the limits of integration I'm getting from here. So 0 to 1. And then 6t plus 12 dt. And so we take the integral of 6t. So let's see, 3t squared plus 12t. Evaluated from 0 to 1. And so we're going to get 3 plus 12 when we put in the 1, and 0 when we get 0. So 15. Oh, okay, I was looking at the wrong problem earlier, which is why I couldn't find the solution, but this is correct. Notice, I just want to point out one thing here is that when you have an integral of this form with a square root in it, it's really hard to get something that integrates nicely. In fact, a lot of times this creates the conditions for having to do a trig sub in order to do the integral. So be grateful when you get, most of the book's problems are going to be nice and straightforward like this and work out quite nicely. But just be aware that normally when arc length is going to be one of those integrals that's going to be hard to solve. Okay, the next thing I want to talk about is just the arc length function. So what this is when we calculate arc length, when we're looking at this here, this is a definite integral. And so then the answer is a scalar. However, if we're talking about the arc length function, this is going to be still a scalar, but it's a scalar function. In other words, we're going to have a formula for arc length, and we can, t will be our variable. This u is just a dummy variable. So what we have is a definite integral, but we get a function because we're putting in as our last endpoint the t. And so then we can calculate the arc length at time t, and then put in t for specific instances. So let's go ahead and do this work this next example. So we want to find the arc length function for r of t equals 2t. Okay, so we're going to need to find the first derivative. And that's going to be 6 cosine 2t negative 6 sine 2t So that's our prime. We're gonna change it to u. Actually, we're gonna find the magnitude first. So we've got square root of 4 plus 36 cosine squared into t plus 36 sine squared 2t. And if you factor a 36 out of here, you should see that that is the Pythagorean identity. So this is 36 times 1. And so what we get is square root 40, which is 2 root 10. Now, if we're going to find the arc length function, s of t, then what we need to do is take the integral from 0, so typically a equals 0, just because that's our initial time. So if we're starting at t equals 0, that's pretty normal. And then you know, t is the amount of time that passed after 0. So we're taking the integral from 0 to t, and now we're going to plug in the magnitude of r prime of t. So that is 2 root 10. And there isn't a variable in there. If there had been a t in there, we would have replaced it with u. We don't want one of our limits of integration to be the same as the variable, as the moving part. So that's why we use u. And so we get 2 root 10 times u evaluated from 0 to t, which is 2t root 10. And that's our arc length function, and this is the distance traveled. After time t. Where on r of t are we after traveling a distance of pi root 10 over 3? So this pi root 10 over 3 that's s. And so we set s equal to 2t root 10. Solve for t. So pi root 10 over 3 equals 2t root 10. If we divide both sides by 2 root 10, we're going to have pi root 10 over 3 times 2 root 10. Which is pi over 6. If we want to, so this is extra, we can compose let's see, r with t of s. I'll show you what that looks like. So we have t is s over 2 root 10. And that one right there is equivalent to this. I'm getting this from here. Just solving that for t. And so what we can do, let me scroll up a little to look at what r is. Here's our r. And so if we compose those two functions, we're putting that t, the t equals s over 2 root 10 into r, okay? So what we're going to get is an r that's in terms of s, which is arc length. And all we're doing is we're rewriting r, so 2 times t, instead of 2 times t, let me put what r of t is right above here so that I can scroll down a little. Let's see, 3 sine 2t, and then 3 cosine 2t. Okay, so 2 times t is 2 times this thing, and so the 2's reduce, and we just get s over root 10. For the second one, again, when we put in that t value, we're going to get 3 sine of s over root 10. And then for the third component, we've got 3 cosine s over root 10. And by composing these functions, we would be able to do that part B by just substituting this s value here into this vector, and then we would get the point. Let me actually backtrack a little bit. I think I might need a little more room here. Let me just go in a different color so we can see it. I don't know that I answered the question in part B. It says where, and I answered pi over 6, and that's not where, that's when. So what I would want to do is from there, where would be if I put in to the one that I have in terms of t, so r of t, not r of s. R of s is an alternative way to get this answer, okay? So this is r evaluated at t equals pi over 6. And what we should get is the vector pi over 3, 3 root 3 over 2, 3 halves. And so that's the point that we are on the curve after traveling the distance of pi root 10 over 3. The next topic is curvature. So what we have here is a definition that isn't, even though it looks like a formula, it is not a useful formula because calculating this derivative isn't practical. Okay, so we use Greek letter kappa to represent curvature, and it is the magnitude of the rate of change of the unit tangent vector with respect to change in arc length. If you haven't seen this abbreviation, this is with respect to. And so we're measuring the rate of change of the unit tangent vector as it goes along this curve. So let me take a moment to look at this curve and kind of answer intuitively, where is the curvature greater, at P or at Q? Now, if we look at the unit tangent vector here, and we look at its rate of change with respect to curvature, I think it's pretty intuitive to when you compare it to here to the tangent at Q, is that the curvature at P, put parentheses, is smaller than the curvature at Q. And hopefully that is somewhat intuitive. There's another way of looking at this, which is, I think, helpful, is that curvature is inversely proportional to the radius of the oscillating circle. It's osculating, not oscillating. So let me back up here. Osculating circle. So the oscillating circle is, this word osculating actually means kissing. And so it's kind of like a tangent circle. It's like the best fit circle that takes up as much of the curve, if that makes sense. So here our radius is, I'll call it capital R. And the oscillating circle over here at Q, we'll call that little r. So the larger the radius of the oscillating circle, since you have this inverse proportionality, then the smaller the curvature. And we can assess this by looking at the, you know, it's exactly what we'd expect it to be when it comes to the measuring curvature. Okay, so what I gave you before up here, again, not a formula. For the formula, you want to use these ones, the practical forms. So we have a couple. We have R3 and R2. And so let's go ahead and do a quick example. Find the curvature function. Okay, so for A, we're going to use this formula here, this one. I don't want to find the unit tangent vector or the derivative of the unit tangent vector. If it were in the context of a problem where I already found the unit tangent vector, then I would use this formula. But since I don't have it, I'm going to use this second formula. It's more practical. So let's start with r prime. That's 2t negative t squared. And then we want second derivative. 0 to negative 2t. And then we're going to want the cross product. So let's put in Ri, J, and K. And I'll do the cross product right here since I already lined up my derivatives. Okay, so let's see. For negative 4t squared. Minus negative 2t squared. So that's plus 2t squared. The j component is going to be 0 minus negative 4t, so 4t. And then the z component is going to be 4 minus 0, so just 4. And let me double check and make sure that I got these correct. I did. Okay. So now we want to take the magnitude. Again, we're looking up here. So the magnitude of r prime crossed with r double prime, that's going to be the square root of 16t to the 4th plus 4t to the 4th. Whoops, I think I screwed that one up. I totally screwed that one up. Don't tell anybody. This is 2. You know what? I just realized. So this very first component here, they're like terms. So this is negative 2t squared. So let me try this one more time. We've got 4t to the 4th plus 16t squared plus 16. And now what we need is the denominator, right? We need the r prime, the magnitude of r prime cubed. So let's look at the magnitude of r prime. That's going to be the square root of 4 plus 4t squared plus t to the fourth. And this is the square root of t squared plus 2 quantity squared. So t squared plus 2 is the magnitude of r prime. And so if we put this into our formula now, all the different pieces, then we get curvature at time t, or it doesn't need to be time, but whatever the parameter is. And let's see, I want my numerator is right here. I can definitely factor a 4 out and then other stuff, so let me do that. So equals, if we take the 4 out, then we're going to have t to the fourth plus 4t squared plus 4, and then that, this right here is this t plus 2 squared. So I'm going to get 2 times t plus 2 in my numerator, and then t squared plus 2 in the denominator. And t squared plus 2 cubed, and I'm checking my notes to see if I did this correctly. So 2 over, this should be t squared plus 2 in the, okay, so let me, I just see where I made my mistake here, and that's right here. This is t to the fourth, so that should be t squared. So this should be t squared. And then that means that our k of t can be reduced. So our curvature at t is going to be 2 over t squared plus 2 quantity squared. Now for part B, find the curvature at a specific point. We just need t. Oops, that should be a 3. And so all we need to do is just set our x component equal to the x component of the point and solve for t, and then we just need to repeat it for each of the components and make sure that the t we pick is consistent and lands us on our curve, and then we're going to plug that into our curvature formula. So we've got 2t equals 2, we've got t squared equals 1, and then we have negative 1/3 t cubed equals negative 1/3. And we can see by inspection t could be plus or minus 1 if we look at that one. But if we look at all three, we can see that t needs to be a positive 1 in order for all three to be true. And so then k of 1, that's going to be 2 over 1 squared plus 2, so 3 squared, so 2/9. And that's the curvature at the point 2, 1, negative 1/3. The next example, we want to find where the curvature of this two-dimensional function is at a max. So notice this is R2. And at a max, means this is an optimization problem. So our goal here is to find where the curvature is max, and the curvature is at a max. I can't spell when, but I'll try again. When k prime of t equals 0. As we know, if we have a curvature function, we know that our maxes and mins are going to occur when the derivative is 0. So the curvature function is not the same as the function, okay? So just keep that in mind. We don't want the maximum of the curve. We want the maximum of the curvature, okay? Which may or may not be different. Actually, you can guess on this one because what we have here is a parabola, right? Let me see. So our y equals 2x minus x squared. I think I'd need to, I'll graph it later. I don't feel like graphing it right now. Well, I'll do it on GeoGebra in a second. Okay, so let's first start by finding the curvature, and then we're going to want that formula from earlier. So let's scroll up here and see what it is. The one we're looking at is right here for the two-dimensional one. Okay, so we have the magnitude of the second derivative over that thing. Okay, so we want the magnitude of the second derivative over, this is 1 plus the first derivative squared, and then this whole thing gets raised to the 3/2 power. Okay. So we're going to need, so first of all, f of x is our 2x minus x squared. So f prime of x is 2 minus 2x. And second derivative is -2. So notice that this numerator here, those are absolute values. The magnitude of a scalar function doesn't make sense. So in this case, we know contextually that we mean absolute value of the second derivative, which in this case is just +2. So let's plug into our formula. So we have 2 in the numerator, and then in the denominator we have 1 plus the first derivative squared. So here's the first derivative, and I need to square it. So I'm going to go ahead and square it right now while we're at it. So 4 minus 4x plus 4x squared. And this is all going to be raised to the 3/2 power. And what we get is 2 over, let's write this as 4x squared minus 4x plus 5 to the 3/2 power. And I think I did screw something up, and I'm pretty sure I know why, or I know what I did. So here's the problem right here, and here's the correction. I needed to double that product, so that should be an 8, not a 4. And so this should be an 8. Okay, so this is the formula to find the curvature of this parabola. Okay, and it's going to depend on x. I may need more room, but that's okay. Let me go ahead and answer this question really quickly because that's an easy one. What does k equal 0 imply? 0 curvature. If you had to guess, I'm pretty sure most of you would guess linear. And you would be right. Okay. So going back to this previous problem here, we want to maximize k of this time x. We don't have a parameter, so we're going to take the derivative. So we need product rule. So that is, I'm sorry, quotient rule. I guess we could use, you know what? Let's use product rule. This is the same as 2 to the 4x squared minus 8x plus 5 to the negative 3 halves. And then we don't need any of that. Okay, then we can just do the, okay, so we've got 2 times negative 3 halves times 4x squared minus 8x plus 5 to the, we have negative 3 halves power, so we're going to reduce that by 1 and get negative 5 halves power. And then we need to use chain rule to multiply by the derivative of the inside function, which is going to be 8x minus 8. And that needs to go into parentheses. Okay, so now what we have is in the numerator, we have this, change. We have this negative 3 and we have this 8x minus 8. So I'm going to go ahead and factor out the 8. So I'm going to have negative 24 times the quantity x minus 1 in the numerator. And in the denominator, I have 4x squared minus 8x plus 5 to the positive 5 halves. Since here, it's hard to see, but there's a little negative sign in front of there. Let me undo that, it made it worse. And so if we bring it down, there's a negative sign there. It's just hard to see. Okay, and so in order to find the maximum value, we need to find where we have our horizontal tangents. And so k prime of x, we're going to set that equal to 0. This will give us maxes and mins. Of course, the only thing that matters is the numerator, because the denominator doesn't determine whether a number is 0 or not. And so then we just get x equals 1. And that's where, in this case, the max occurs. We could check that. I'm going to check it graphically, but we could check it by doing a sign graph. You guys remember this, I'm sure. So if we look at f prime for numbers smaller than 1, this might be hard. I think we're increasing. I think we're positive in that case. We can say, we can say this denominator is positive because it has a square root. Okay, this 2 here means that we have a square root. So we can just assume this denominator is positive. So then the only thing that we're looking at is for k prime. I wrote f, but this is k. So when we're looking at the curvature, we only need to look at this term here, that expression, the x minus 1. And so x minus 1 before 1 I take everything back. We just need to look at this negative is going to screw things up. Okay, so when x, this is x, when x is less than 1, when we plug into the curvature, we're going to have negative 24 times a negative value divided by a positive value. So that's a net positive. And then after the 1, everything switches. And so that's a net negative. So that means that the tangents are increasing here and they're decreasing here. We're doing this. And this right here is actually the vertex, because we know what we have is actually a parabola. So let me just graph it really quick. 2x minus x squared. I'm going to open up, actually, I'll let you guys graph it and look at it. I'm going to go ahead and end this now because I think it's super long, and then I will post part.